Welcome to section 6.7, inverse relations and functions. So what we're going to do is we're going to think about the order of operations, and then we're going to do those order of operations backwards to create the inverse. So the inverse is always opposite of doing an operation. So for example, addition is an operation, the inverse is subtraction. Square root is an operation in math, and the opposite is squaring. So here we go. What are the order of operations here? Something is being multiplied, and then something is being added. So we're going to multiply by 2 and then add 3. So the inverse would be to do the exact opposite of this. So what did I say? Multiply by 2 and add 3. So I'm going to do this 100% backwards. So I'm going to say y is equal to subtract 3, because that would be the opposite of the addition, and then divide by 2, because that would be the opposite. So that's the inverse. So it's like, okay, this seems kind of magical. How in the world do we come up with this? Well, to find the inverse, we need to make the input the output and the output the input of the function. You put in a number x and you get out an answer y. So this is the input and this is the output. But the inverse would do it all in reverse. Kind of like if you drive to a friend's house and you make a series of left and right turns, when you come home, you're going to make the opposite set of turns at each intersection. So the input is the output's the input. The x comes over here where the y is, and the y goes where the x is. So to find the inverse, which we've already found, the algebra way to do it is to switch x and y. So we switch x and y, and then we solve for y. So switch x and y, solve for y. That's how you find the inverse. To solve for y, I have to do opposite things. So I'm going to move the 3 over by subtraction. So subtract 3 on each side. So x minus 3 is equal to 2y. X minus 3, hey, that looks familiar. Then I would get y by itself by dividing by 2. So x minus 3 over 2 is equal to y. If you were to graph this, it's not so easy to graph because you have to have like a slope, and a y-intercept is easier. So I'm going to distribute the division of 2. So this is probably a better answer. 2 divides into 1 to make 1/2 x, so that's the slope. So slope of 2, slope of 1/2. And then negative 3 over 2 is negative 3/2. So I distributed the division. So this would be an answer to type into a graphing calculator or whatever. Now we're going to see what this looks like in a graph form. So this is the original line right here. That's a line because it's x to the first power. And then down here we have a line too that is a line as well, which is the inverse. So everything is switched. The order of operations has changed. So multiplying by 2 became dividing by 2. Subtraction or addition became subtraction. And then even the order in which you do it switched, because you would multiply first. Well, here there's parentheses and you're going to divide last. We add second after we multiply. Here we're going to subtract first. So everything switched 100% to make it the inverse. Now we're going to graph this. So where's my handy piece of graph paper? To do this, we will create points. Instead of doing y equals mx plus b, I'm going to create points and just kind of show you the actual switching of x and y. So do the old pre-algebra version of this. I like 0. 0 goes in, 3 comes back, so 0, 3 is the original. I'm going to do 2. That would be 7. Negative 2, that'd be negative 4, negative 1. So there's our 3 points. Well, guess what? I now have the original, right? The original looks like org, I guess. I always abbreviate original that way, it's okay. That's the original. And then I already know the inverse table. So I can go x and y, and I have the inverse table instantly, because how do you take the inverse? Well, you make the input the output, and the output the input. So it's 3, 0, 7, 2, negative 1, negative 2. That's the inverse table. And if I graph these points, I'll get the original graph and I'll get the inverse graph. And we'll see if that matches a slope of 1/2 with an intersection of negative 1.5 or negative 3/2 on the y-axis. So here's my piece of graph paper that I'm putting in here, and my points. I can see it all at the same time. So 0, 3, 1, 2, 3, 2, 7 would be about there, and negative 2 down 1. So there's my line, 1, 2, up 2 over 1, up 2 over 1, up 2 over 1. So it has a slope of 2. Makes sense. Now we're going to do the inverse. 3, 0. The inverse points are right here. Remember, I wrote inverse. The inverse points are here. 3, 0, 1, 2, 3, 7, 2, and negative 1, negative 2. So does that match what we had before? And oh, this kind of works right there. Yep, that's the point right there, because it's a slope of down 2, back 1, and the slope of up 1 over 2, slope of 1/2. So this is a slope of 1/2 because it's up 1 over 1, 2. See, it hits in the half there because there's the negative 3/2. So it's down 1, down 1.5. So if you start here and you go up 1 and over 2, up 1 and over 2, so you keep hitting all those half spots. So that is the line y equals 1/2 x minus 3/2. And this is the line y equals 2x plus 3. And they're inverses of each other. Notice the symmetry that's happening here. And also this point here, 1, 2, 3, 1, 2, 3. Negative 3 comma negative 3 is the intersection between the two lines. And that totally makes sense, because if you switch these, the input and the output and the output and the input, it stays the same. It's a common point between the two inverses. Then all the other points flip across the line y equals x. So there's an invisible line here. It's a line of symmetry. This is the line y equals x, and that is a line that all of these points flip across. So notice this was 7, 2, and then 2, 7. They're mirror images of each other. 3, 0, 0, 3 are mirror images of each other. This negative 1, negative 2, and negative 2, negative 1 mirror images across that symmetry line. And then there's no flipping there because that's actually on the mirror. So let me make this a little bit clearer right there. It's y equals x. That's the line of symmetry for every inverse problem. And that's the original that we worked with, and then this is the inverse, and it flips across. Okay, next example is the same kind of thing. We're going to do the original graph and the inverse. So we're going to handle this the same way. We're going to create a table. This is a parabola. It's y equals x squared minus 4. Let's come up with the equation too. So here's the equation. And then we'll come up with the table and make the graph and all that business. So we switch x and y, solve for y. Switch. Solve. X plus 4 is equal to y squared. Now we have to get y by itself. So we switched x and y, and we solve for y to find the inverse. Square root, square root. Now don't forget, when you take the square root, you have to consider the plus and minus solutions. So you get plus or minus the square root of x plus 4. So there's actually two equations built in there, a positive square root equation and a negative square root equation, which is why this is in this chapter, is because the inverse of the x squared is the square root function. That's the connection. And we've done square roots and we did squares earlier in the book. So this is the inverse ideas of each other, and it all matches with the chapter because the chapter was about radicals. So I'm going to make a table off of this, and then I don't have to make a table of values off of this here because you just switch x and y. But if you want the actual equation, that's the actual equation for the inverse. So here's the original. I'll call it orig this time. This is a parabola. It's been shifted down 4 spaces. So I'm going to put 0 in. because 0 is the vertex. If you did negative b over 2a, because there's no b term, then the middle number there is 0. I'm going to pick 2 and negative 2 on number on each side of the vertex. If I put in 2, I get 4. 4 minus 4 is 0. Remember, these numbers are always the same. And you put 0 in, and you get negative 4. So the inverse would be the flippy of all those points. 0, 2, negative 4, 0, and 0, negative 2. So there's the inverse points, there's the original points. Now let's graph these and see what this looks like. Let's see. Let's graph it. I'll put the graph over here on this side. What I need to do is I need a little bit more space here, so I'm going to pause it for a second. I took some scissors and I cut this out so we could see it a little bit better. So there's my work, there's the original, there's the inverse equation, it's a square root equation, here's the graphs. So the original is going to be 2, 0, which is this way, negative 2, 0, which is that way, and then down 4 spaces, 0, negative 4, that's 1, 2, 3, 4. And I'm going to make myself a parabola. This parabola is right side up, it's a happy parabola. Missed the point there a little bit, just make the dot a little bigger. And then now the inverse. The inverse I'm going to make in a different color. I'll do blue. Blue pen. Kind of hard to see. There, you can see it better. So that's 0, 2, which would be up 2. Negative 4, 0, which is 1, 2, 3, 4. And then 0, negative 2, which is down here. So this point flipped to this point, that point flipped to that point flipped to that point, and the parabola is flipped sideways, so it's a sideways facing parabola. And there we go. So it flips across this imaginary line, and it makes a sideways parabola. Sideways parabolas are not functions, so it's definitely not a function. We talked about what functions were earlier. Now, I'm going to get out a pink highlighter. Somewhere here I have one, I believe. Pink highlighter, where did you go? There you are. I'm finding my pink highlighter. There's the pink highlighter. Now, if you look closely, I just made you all a Valentine. See the Valentine? So if this was February, we'd be set. You still not see the Valentine? There it is. There's the heart. So the two parabolas put together kind of looks like a heart. So the line of symmetry is still there. The inverse is not a function because for each x there has to be one y value. So for this x value there's two y values. So a parabola is definitely a function. But the inverse of a parabola takes the parabola and flips it sideways. So the inverse of parabola is not a function. Now individually, you could graph these lines, or these square root functions here, and you could graph one each individually on a calculator and make it be this way. So you could go like y1 was equal to the square root of x plus 4, and then y2 is the square root of x minus 4. So you could graph them separately, but together you can't. There's no plus minus button to graph them together because it's not a function. You have to separate them to create this actual graph. Now, the last section is checking for inverses. How do we know if something's an inverse? Well, this is the first example. This and this are inverses of each other, but how could I prove that to you? Well, the way to prove it to somebody is to say, hey, if I go 2 steps forward from x, that would be a new spot x plus 2. And then if I go back 2 spaces, that would be like minus 2. Well, if you put that together, x plus 2 minus 2, the 2's cancel and you're back to x. So if you do something and then do the inverse, it takes you back to where you are. So that says that if you can take the function, and then the f to the negative 1 is the notation for inverse function. If you take the inverse function and put it inside the function, you go back exactly to where you started, x. Or if you can take the inverse and put the original function in it, and that should all undo each other, and you should go back to the starting point, x. So you can check a function by either way. This is the composition of function notation that we just recently talked about. So you're going to put the function inverse into the function, or the actual function into the inverse, to prove that it is an inverse, and you get x as your starting point. So we're going to do that here. I'm going to take, this is the inverse, I'm going to take it and I'm going to throw it into the actual function and see if everything cancels out. So y is equal to 2x plus 3. This is the other function. I'm going to throw it in here. 1/2 x minus 3/2. Distribute. 2 times 1/2 is 1, so it's just x. 2 times negative 3/2 is negative 3 plus 3. And look at that. Those cancel out. We get y equals x. So definitely, when you put a function inside of a function that's our inverses of each other, everything cancels out, because it's just a series of doing the opposites, and everything cancels out and you're back to where you started. And my simple example of that is, if you start out at position x and you go forward 2, and then somebody tells you to do the opposite, go back 2, you're back to where you started. You're back to x. All right, this is inverses and functions. We know that if we switch x and y around on a line, we just get another line. And all lines are functions except for a vertical line. But if you take a parabola and you flip it sideways, it's definitely not a function. So that's something to look forward to, but look at is whether it's a function or not.